In today's episode, we're going to deal with dynamic lung volume. Now, in these measurements of dynamic lung volumes, we are going to bring a factor of time into play. So, it can be represented with respect to how fast things happen or what proportion of volume goes in 1 second or 2 seconds or things like that. So, there are various measurements that are there in dynamic lung volume. So we'll start with your forced vital capacity. So in forced vital capacity, what we're doing is at the end of maximum inspiration, vital capacity needs to be recorded. Now the person has to forcefully, as fast as they can, expire out. So they have to expire out as forcefully as they can, as fast as they can. So it should be done very fastly. And the vital capacity that you record is your forced vital capacity. Not much change is going to be there for this value. The only thing is that graph will be slightly more faster. Now let's take a look at that forced vital capacity. So this is us normally inspiring and expiring. And we're going to take maximum inspiration, and from here we are going to expire. This is your vital capacity that is happening. So this is the point. So this volume that you see over here, that is your vital capacity. So here we are asking the person to forcefully expire and as fast as they can. This is the forced vital capacity. This is the volume that is expired. So it is forcefully and fastly. So as fast as they can and as forcefully as they can. That is your forced vital capacity. Now we are going to bring time into this equation. How are we going to bring time into this equation? We are going to see the amount of this total volume that is going on in the first second. So this is the volume and this is time. And if we take this as say 1 second, and we take this as the second second, we take this as the third second. So what we see here is by the end of first second, this much of the volume is gone in the first second. By the end of second second, you see that around this much of the volume is gone in the second second. By the end of third second again, this much of the volume is gone. Are we understanding it? So when we talk about a particular volume over here, which was from here till here, so this total volume is your forced vital capacity. And in the forced vital capacity, initially when we started expiring, in the first second around, this is the volume where that is expired out of the first second. When we talk about second second, it came a little much more. And third second again more was expired. So at the end of first second, that is what is called FEV1. So volume expired at the end of first second, that is FEV1. So this usually comes to 84%, up to 84%. There's a broad range for that. And by the end of second second, FEV2, that is 93%, 93 to 94%. And at the end of this FEV3, the volume would come to 97%. So this FEV1, FEV2, FEV3 are the volumes. But this percentage that you see, that is the FEV1, that volume in out of the FEC. So out of your force vital capacity, how much volume, that volume's percentage that goes in first second, that is your 84%. I hope it's not difficult. I'll just go with it again. So total volume is force vital capacity, and the volume that goes in the first second is FeV1. So there's a particular volume, and if you take FeV1 by FVC, that means out of the total FVC, how much volume goes in the first second. So that percent, when you express it in percentage, that is this. So this is FeV1 by FVC, this is FeV2 by FVC, and this is FeV3 by FVC. So that is what it means. So this means that in the initial segment, 84% of your volume is gone. So maximum is there in the initial 1 second, and then look at the next. By the next, it becomes to 93%, and then later it becomes to 97%. So basically after that, your rate kind of slows. So initially the rate is very fast and it reaches up to 84%. After that the rate slows down. Then it takes another 1 second to go from 84 to 93%. And it takes another 1 second to go from 93 to 97%. So that is where you have to understand this concept of time constant. You'll come across this in many places in physiology. Time constant in exponential graphs. Whenever you talk about exponential graph, that is the time taken for 63% of a change. So for the here time constant, for the whole vital capacity, 63% of the vital capacity change. That is a time constant, and that means in the next time constant, if you add another time constant time period, that means next 63% of remaining happens. In the next time constant again, next 63% happens. So like that, it is a gradual exponential process like that. Understood? So that is time constant. This is force vital capacity, FeV1 and FeV1 by FVC. The percentage of FVC that goes in 1 second. The percentage of FVC that goes in the second. So that is the whole concept of this. So this determines how fast you can expire. So time has come into play over here. So that is your force vital capacity. So that is about this. Now we need to go to something called flow rate. So here it was volume in the x-axis and time in the y-axis. So this was the curve that we just saw over here. Now in another graph, we will try taking the flow rate, and in the y-axis we'll take volume. So here we'll take the flow rate, and here we'll take the volume. So here it was volume here and time here. Here we'll take flow rate here, volume over here, right? So when we talk about volume, total lung capacity is the maximum volume that is there. We'll take this as the total lung capacity, and if you expire from there, that can go till your residual volume. Beyond that it cannot go. So this is the total lung capacity till residual volume. So when we inspire, what is going to happen? From residual volume we are going to inspire. And here this is the flow rate, how fast it goes. Okay, it's nothing else, don't get confused there. This is the volume, and this graphical representation here only denotes the rate of flow, how fast it can go. So let's take a look at inspiration. We try inspiring. Initially it's slightly slow, but then somewhere in the middle it picks up its speed, and towards the end it slows down again. So just try it again. You try it again. Can you see how initially it is slow, towards the middle it picks up its pace, and towards the end again it gradually slows down. So that is what happens to the flow. Initially over here, from here it goes somewhere, and towards the middle it increases, and from here by the time it reaches total lung capacity it slows down. This is the inspiratory loop. So it increases gradually and then decreases the flow rate. Let's think about expiration. Try expiring as forcefully and as fast as you get. So initially we had seen how in the first second 84% of the volume is gone in the first second. So that means that initially there is a very fast flow rate, but later you know that the critical closing volume comes and it starts collapsing and the flow rate decreases later on, and we can see it from this. So that is what happens over here. Initially there is a time when it becomes maximum fast. So the flow rate will be maximum initially at one point, and then the flow rate keeps reducing. So this flow rate over here, which is the maximum, that is what is called the peak expiratory flow rate, PEFR. So there are instruments like a small cannon, you can take it like that asthma inhaler, that sort of thing. You can take it and flow into it, and it measures how fast it can go, the maximum, not anything else. Maximum force to which it can go, it can be measured. That is the PEFR, peak expiratory flow rate. So this is the maximum speed at which it can happen. So you see how it is happening in the initial part of expiration. Now the same graph, if you try to interpose over here, by the end of 1 second, 84%. So we'll take the volume here, this is the vital capacity, and from here around 84% will be gone in the first second. Next second around 93%, 94%, and the last second again the remaining 97%, and then whatever is remaining is later after that. So this is how we can interpose that diagram into this. So this will be FeV1. So actually this is the volume. So this is FeV1, FeV2, FeV3, and this is still residual volume. So this volume in fact ultimately was your vital capacity. So you understand this? So we tried interposing that into this. We understood what peak expiratory flow rate is. We understood what FeV1, FeV2, FeV3 and all that is. And we understood what happens in inspiration, what happens in expiration, and how different it is. So this is where another set of questions can come. What is the difference between obstructive lung disorders and restrictive lung disorders? So in obstructive lung disorders, we had seen about the equal pressure point and all that. So in obstructive lung disorders, the collapse happens, expiration is affected, inspiration is not affected. So we are not going to take this into consideration anymore. We'll just do over here. We'll forget about this because inspiration is not much affected. Okay, so next is your expiration in obstructive disorders. Tell me what is going to happen in obstructive disorders. You inspire normally, volume is there, total lung capacity is okay. Yeah, when you expire, it cannot reach the maximum speed because it is closed down early. So this peak flow will fall. Because of the collapse that is present, this peak flow rate is going to drop. That is one thing that will happen. Second thing that is going to happen, you try expiring as much as you can, but because of the collapse, there is more amount that is remaining than normal. So instead of it ending here and this being the residual volume, now there is more retained volume that is remaining at the end of expiration because of the collapse in chronic obstructive diseases or any obstructive disease. So because of the air trapping, now this will be the new residual volume. And on top of that, inspiration is not affected much. So because the inspiratory process is not affected much, the amount of air it can take, the inspiratory reserve volume is not affected much. So So that still goes about normally. That is why that total lung capacity seems more beyond the normal value. Understood? So the residual volume was there. The peak flow decreased in chronic obstruction. Right? In obstructive disorders, peak flow decreased because of the collapse. Flow rate decreased because it became more narrow. And because of closure, there is some sort of air trapping even at the end of expiration, which is more than normal. So there will be more volume that is remaining than normal. But since the inspiration processes are not affected much, the amount of volume that is taken is normal. So if this was the amount of volume taken, when you, even if it starts from here, you still take that much amount of volume. You try expanding it as much as you can. So that will seem a little, not this much, slightly more. So now from here, it has gone up. Initially it went, and that speed went in this instead of this, and from here it drops. So this is what happens in obstructive disorders. So what happened in obstructive disorder? Because of air trapping, this gets shifted slightly to the left side. Left side means more volume, and your flow rate decreased. Vital capacity is not affected that much. Slight decrease in vital capacity may be there. As I had mentioned, it might not exactly come over here. Instead, it will come over here. So vital capacity might be slightly decreased, but not that much. But this is decreased definitely. This is what happens in obstructive disorders. When we take a look at restrictive disorders, what is the problem there? Expiration is not the problem there. The problem there, even there, the flow rate is not changed. There's no collapse, things like that is not taking place. So the flow rate is not affected much. The problem there is about how much can be accommodated. There's a restrictive sort of disorder. Either some problem is there in the respiratory muscles, or there is some problem with the chest wall, or the lung parenchyma, like interstitial lung disease. So because of that, there is a restriction to how much the chest can expand. So what is going to happen here? What is the primary problem that is going to be faced in restrictive disorders? This total lung capacity will go down. And if this was a residual volume, this will slightly be here. And if this was a vital capacity, that vital capacity will slightly be lesser. But the peak flow is almost that level. It's not decreased that much. It will be slightly decreased, but the decrease won't be that much. So somewhere close to it. And this is your restrictive disease. So over here, this is the flow rate, and this is the normal. This is the obstructive disease, and in restrictive disease, you understood what happens. So this is the difference. The same diagram can be put over here as well. When you put over here the same diagram, what is going to happen? In obstructive disease, what is going to happen? Initial FEV1 is normally 84%. But because the flow rate is reduced, it won't be 84%, it will be lesser. So in the first second, if it was here, now this graph would go more outside. That means the graph would be like this. So in the same time of 1 minute, see, only this much percentage was gone instead of this much. So the FEV1 dropped. The peak expiratory flow rate dropped. So that is what happens in obstructive disorders. When we talk about restrictive disorders, what is the change? The flow rate is not affected much. The problem would be this vital capacity. It will not reach till here. But over there, the same graph would start from somewhere lower. It will start from here and join like this. That is restrictive disorder. So vital capacity is affected in restrictive disorders. the FEV1 or peak expiratory flow rate, these are affected in your obstructive disorders. So this is one major change that is there.